Hello everyone, I'm Akif and today we're going to discuss about first order logic and artificial intelligence. It's going to be our second lecture related to artificial intelligence and let's start. So it is all about subject and predicate. We take a sentence, an English sentence, and then we try to find out what is the subject in that sentence and what's a predicate in that sentence. Now, let's have a look at Sweden is beautiful. In this sentence, Sweden is a subject and is beautiful is a predicate. Now, let's have a look at another sentence. Here, x is an integer. So, x will be the subject and is an integer will be predicate. Now, let's move forward. X is an integer. And we have our own representation when it comes to first order logic. For example, if we have to represent x as an integer, we will represent it like this. Let's take this sentence into consideration. It will be represented like this in first order logic representation. X is an integer. Or we can also represent it like this in short. So similarly, if we have to write x is beautiful, we'll write it like this. X is beautiful. So here x was a subject, beautiful is a predicate, and let's now have a look at this thing, which is Sweden is beautiful. So we will replace x with Sweden is beautiful. Now, we have some operators and quantifiers in first order logic, and you might be already aware of some of these operators, which is like not A. Here, these literals A or B or C, in first order logic, it will be a sentence. For example, A could be it's raining. Then if we have to represent it is not raining, that will be not A. So if it's not raining, that will be represented with not A. Then if we have a conjunction of sentences, like two sentences, it's raining and it's cold. A will be, for example, it's raining, and B will be it's cold. So a conjunction of A and B will be represented like this, A and B. Similarly, he is a boy or she is a girl, that will be represented with this. If it's raining, the street is wet. Implication will be represented with this symbol, which means if it's raining, the street is going to be wet. So when we have statements like if, then, it will be represented with implication. If and only if. For example, if I work hard, only then I will be qualifying this exam. That will be represented with this operator, and it's called equivalence. So when we have and, it's called conjunction. We have or, it's called disjunction. When we have implication, we will be having this kind of symbol, and then we have equivalence. Now, there are some additional things in first order logic apart from the operators which we discussed. It's universal quantifier, which is represented with this, and this will occur at the times when we will be dealing with sentences like all or every or everyone. And we have existential quantifier, which is for some, or this kind of quantifier is going to occur when we have words like some. Okay, so let's have a look at another thing which is called universe of discourse. Universe of discourse is going to be something with respect to which we will be dealing with these sentences. And let's take these examples, like every lion is mortal. So let's assume that we have a universe of discourse. It's also known as domain of discourse. For example, we have a universe of discourse, and in this universe of discourse, each and every entity is a line. For example, L1, L2, L3. These are all lines. So with this, if you look at this English sentence, it says that every line is model, which means that if I take this L1 out and I am talking about L1, then L1 is model. Similarly, if I take L2 out and talk about it, L2 is model. Likewise, if I say and talk about L3, then L3 is model. Now, if you look at this, that L1 is model and L2 is model and L3 is model, because it says that every line is model. So we could represent from the previous discussions, which we discussed about the representation of the first order logic. If we have to represent L1 is model, we will represent it like this: L1 is model. Then and L2 is model. Similarly, again L3 is model. Now, if we are having so many lines inside this universe of discourse, then it becomes very, cumbersome and lengthy to write all those where we include this and operator. So it could be very large, and it becomes lengthy and time consuming. And for that, we have a single statement, because here mortal and this skeleton, for example, this skeleton mortal gets repeated. Mortal gets repeated. Mortal L1, mortal L2, mortal L3. So this gets repeated. So instead of writing so many statements, we can replace it with a single, which means that every X, which in this case means lion, is mortal. So this is how we represent for all, or everyone. Every X is mortal, and in this case X means lion. Now let's have a look at this another example, which is some cats are gray. And let's take a universe of discourse where we have only cats. C1 is a cat, C2 is a cat, C3 is a cat, and it can go on and on. Now, if I take this cat out, okay, it's not necessary that this cat will be gray. So anyone could be gray. C1 could be gray, or C2 could be gray, or C3 could be gray, or C1 and C2 could be gray. So the best operator that fits in this condition is R. So we could represent it like this: C1 is gray, or C2 is gray, or C3 is gray. Okay, let me write it here now. If we want to represent in terms of first order logic representations, how would we represent it? It is just like this: C1 is gray, or C2 is gray, or C3 is gray. Now if we have many, for example infinite number of cats, then it can go on and on. So C1 could be gray, C2 could be gray, or C3 could be gray. Now, when we have that anyone could be gray, at least one or more than one, for that we have this representation which is called as uh, there exists at least one cat which could be gray. So how would we represent that? This C1 would be replaced with X, which because C1 is the variable, because this entity, this subject is variable here. They are varying, but gray is remaining constant everywhere. This skeleton is remaining constant everywhere. So we represent this thing, which is a variable, with X. And from the above statements, we realize that either one could be gray or more than one could be gray. So we could replace it with something which means as there exists at least one X or cat which could be gray. That is represented with this quantifier, and it's called as existential quantifier. Now, in many cases, when you will deal with first order logic, when we have a universal quantifier, we would very often see this implication operator. And when we have existential quantifier, we will get to see and. Okay, now let's have a look at the previous two examples, which is every lion is mortal. Let's write it here. Every lion is mortal. In the previous case, we had a universe of discourse where we had only lions. Now let's shift our gears and change our universe of discourse a bit. We assume that it's a universe of animals. We have all the animals, we could have all the animals over here, and there is this animal A1, there is this animal A2, there is this animal A3, and it could move on to infinity. That number we could have. So there we have to check two conditions. If I take this A1 animal out and I am discussing about this animal A, according to this sentence, we have every lion is mortal. If I take this animal out and if it happens to be lion, okay, if it happens to be lion, someone took this animal out and it happened to be a lion, then according to this statement, it has to be mortal. So if it's a lion, then it will be mortal. That's what this sentence over here means. Now let's represent this. For example, if A1 is lion, then A1 is mortal. And if A2 is lion, then A2 is mortal. Again, if A3 is lion, then A3 is mortal. So in the previous example, we were talking about only lion, X. Now we have two things. We have two representations. For example, if I have to represent A1 is a lion, I could represent it like this. A1 is a lion. And A1 is mortal. I would represent it this like this. A1 is mortal. Similarly over here, A2 is lion, then A2 is mortal. It is along with and. A2 is model because A A3 is model because A3 was a lion. So this will go on and on and on like this if we have many such statements. So here this skeleton is remaining constant, which is lion and mortal. So the only thing that's varying is inside these parentheses and inside these parentheses, and both of these are just a single entity. So we would replace it with a variable x. Let me represent it here. So we would represent this with variable x. So if x is a lion, then x is going to be a mortal. And we're talking about every lion is mortal. So for all lions, if for all x, if x is a lion, then x is mortal. That's how we would represent this. And this implication statement only happened when we changed the universe of discourse, where it had to satisfy this condition where I took an animal out of this universe of discourse, and this animal happened to be a lion. And if it's a lion according to this statement, then it's for sure it's going to be mortal. So when we discussed this problem, which was every lion is mortal, we found that it could be represented with this quantifier, which is called universal quantifier. And if x happens to be a lion, then it is mortal. There's an important thing to note is that if this universal quantifier occurred, then along with this we're going to see an implication. Okay, now let's discuss another problem. So this problem is some cats are gray. Now let's again assume that we have a universe of discourse where we have all the animals. We have animal A1, A2, A3, so on to infinity. If we have infinite number of cats, then according to this statement, some cats are gray, which means not all cats are gray. So according to this statement, some cats are gray, which means that not all cats are gray. And if we take this animal A1 out and we found that A1 is gray, sorry, A1 is a cat, and we also found that A1 is gray, then only then this statement is true, which means that A1 is a cat and it has to be gray. Similarly, if we took A2 out and found that A2 is a cat and A2 is gray, then the statement is true. Again, if we took A3 out and A3 was a cat and A3 was gray, then this statement is true. And we also found in the previous examples where we had this case of sum that there is an or occurring between these statements, which is like A1 is a cat and A1 is gray, or A2 is a cat and A2 is gray, or A3 is a cat and A3 is gray. So you might be wondering why this or is between these statements. The reason is this word some, which means that anyone could be gray. Either A1 could be a cat and A1 could be gray, or A2 will be a cat and A2 is gray, or A3 is a cat and A3 is gray, or A1, A2 both are cats and they are gray. So it means that at least there is going to be one animal which is a cat and it's a gray. Now let's try to represent it in the form of uh, you know the first order logic representation. Now, if we have to represent something, A1 is a cat, we can represent it like this. A1 is a cat and A1 is gray. Then again, we know that there is OR. A2 is a cat and A2 is gray. Or A3 is a cat and A3 is gray. It can go on and on if we have more animals who are cat and are gray. So it becomes cumbersome if we keep on writing like this. So it becomes cumbersome if we keep on writing this on and on, all the way up to infinity. For example, if there are infinite number of animals which are cats and are gray, so there has to be something which uh, can represent it in a single statement. For example, here in all these cases, cat and gray is constant, cat and gray is constant, cat and gray is constant. The only thing that is varying is A1, A2, and the A3. Now we'll represent it with a variable which is like this. X is a cat and X is gray. Okay, and we know that there is at least one cat which is there is at least one animal which is a cat and is gray. So that is represented with existential quantifier, which is there exists at least one X which is cat and is gray. And there's another observation that we get to see here is that with existential quantifier we saw an and operator. Okay, now let's utilize this in our problems. Suppose we have all frogs are green. All frogs are green. So here where we see all, okay, and we're taking a universe of discourse where we have all the amphibians. So if A1 is an amphibian, A2 is an amphibian, A3 is an amphibian, then if A1 is a frog, and it's for sure it's going to be green because all frogs are green. So we will represent it with this. X is a frog, therefore X is going to be green. If X is a frog, then it's for sure it's going to be green. And where we have to represent here what's called as all. So for all we represent it with universal quantifier. So for all X, if X is a frog, then X is going to be green. So that's how we solve this statement. Every student in this college has visited Spain and Portugal. So here is every student in this college. In this college. So if this is a universe of discourse which contains all the students from all the colleges, and if A1 is a student of this college, And if A1 is a student of this college, and if we represent it with this, A1 is a student of this college. So suppose this means A1 is a student of this college, then we're going to represent it like this. A1 is a student of this college. And if we have to represent A1 visited Spain, we represent it like this. A1 visited Spain. Then if we have to represent A1 visited Portugal, we represent it like this. A1 visited Portugal. So according to this statement, if every student in this college has visited Spain and Portugal, so according to this statement, every student in this college has visited Spain and Portugal, which means that if A1 is a student of this college, then it's for sure that it has visited Spain and Portugal. How would we represent this? A1 is a student of this college, then it's for sure that it has visited Spain and Portugal. So this was for A1. A1 is a student of this college, then it's for sure he has visited Spain and Portugal. Now, what if every student in this college, every student in the universe of discourse is a student of this college? Then it's for sure that all of them have visited Spain and Portugal. How would you represent this? We know for statements like every and all, we have universal quantifier. Therefore, we will represent it this like this. For all x, if x is a student of this college, then x has visited Spain and x has visited Portugal. Now let's try to solve this problem, which is some prime number is even. There are two things. One is prime number, another is even. So it's not necessary that every prime number is even. Uh, Only some prime numbers are even. So let's take a universe of discourse where we have a bunch of numbers like n1, n2, n3. And if we took n1 out, and if it was a prime number, and if it was even, only then this statement is true. Let's represent n1 is a prime number and n1 is even. But this is for one number. And we saw in the previous examples how we could represent the variables. It's um, x is a prime number and x is even. And we know that there are only some numbers that we represent with for that we represent it like this, which is there exists at least one x such that x is prime and x is even. Now let's try to solve this problem, which is some students love Professor Mark. And for this, let's have this universe of discourse which contains all the human beings. Universe of discourse, and it contains all the human beings. Let's be P1, P2, P3, P4, all the way up to infinity. Now I took P1 out, and what we saw is that P1 was a student, and at the same time P1 loved Professor Mark. So how would we represent this statement? P1 is a student. P1 is a student. And how would we represent P1 loves Professor Mark? let's have a look at this. So in order to represent P1 is a student, it's quite easy. P1 is a student. That's how we will represent this. It's understood because we did some problems which were similar to this. Now, here is this a little bit different approach, which is that P1 loves Professor Mark. So I would represent it like this. P1 loves Professor Mark. Okay. You can write the complete statement like Professor Mark, but I just made it shorter. So if we have to write this statement, some students love Professor Mark, how would we represent that? We know that when we're talking about some, we're going to have an existential quantifier, and along with existential quantifier, there is going to be and. So P1 is a student and P2 loves Professor Mark, only then this statement is going to be true. So how would we represent this? It will be like this. X is a student so we will write it like this. For some X, or it could also be for there exists at least one X, such that X is a student and X loves Professor Mark. X loves Professor Mark. Okay, that's how we represent this. So when we have to solve this statement, which is all students love Professor Mark, so we know that when there's this word called all, then it means we're going to have a universal quantifier, and it means it's going to have an implication with it. So how would we represent all students love Professor Mark? It will be represented like this. For all X, if X is a student, it's for sure that X loves Professor Mark. Okay. Now let's solve this example. All boys are hungry. So we have a universe of discourse that contains all people. And if P1 happens to be a boy, then it's for sure that it's going to be hungry. So we know that there we will have implication. So how would you represent P1 is a boy? We represent it with like this. P1 is a boy and P1 is hungry. Hungry. So here we saw all, therefore universal quantifier is going to be there and an implication is going to be there. So how would we write all boys are hungry? It means that for all X, X is a boy, therefore it's going to be hungry. Now let's solve all successful students are happy. Now we'll be a little quick. We have already understood that for statements where all occurs, we'll represent it with a universal quantifier, and it means that it is going to have an implication along with it. And we also found that when it's uh, uh, occurring with someone or for some, then it's going to have an existential quantifier. So with this knowledge in mind, let's carry on forward and let's try to solve this, which is all successful students are happy. Now, if we have to represent A1 as a successful student, let us represent it with this SU student. like this. Okay, or you can represent it anyway. I'm just representing it like this. So A1 is a successful student. Then according to this statement, he is going to be happy. But let's represent A1 is happy like this. So according to this statement, all students are happy. All successful students are happy. How would we represent this? For all x, x is a successful student. Therefore, x is happy. Now let's try to solve this problem, which is all cheerful people smile. It would be represent like this. Suppose if we have a person A1 and he is cheerful, we'll represent it like this. Okay, if A1 smiles, then we'll represent it like this. So we're solving basically this problem. So it's in the statement, all cheerful people smile. So we're going to represent it with a universal quantifier, which is for all x, if he is a cheerful person, then it's going to smile. For all x, if x is cheerful, then x is going to smile. Someone is marrying. Someone is marrying. There's only one thing involved here, which is someone. Okay, and x is marrying. So if x is marrying, we'll represent it with this. X is marrying. And it's talking about someone is marrying, then we are going to represent it with this. For some x, or there exists at least one x who is going to marry, who is marrying. Similarly, we can solve this, which means someone is fighting. We can represent it with this. X is fighting. And for someone, the quantifier is going to be existential quantifier, which is there exists at least one x, and x is fighting. Okay. Now, so far we discussed a single variable predicate. Now, if we are talking about two variable predicate, then we get to see statements like this: x likes y. If I had to represent it in the form of first order logic representation, then we'll represent it like this: x likes y. I will represent it like this: x likes y. John loves Carla. Then I will represent it like this: John loves Carla. Okay, there are two uh, variables. So Jonathan takes networking. For example, Jonathan takes networking as his subject this semester. Then it's going to be represented like this: Jonathan takes networking. So here the statement goes like Jonathan takes every subject, which makes the statements like Jonathan takes networking. Jonathan also takes artificial intelligence. Jonathan also takes wireless sensor networks. and the list goes on and on and on and on and on. Here what we found is that takes Jonathan remains constant, takes Jonathan remains constant, takes Jonathan remains constant. The only thing that's varying here is this side, which is the subject size. So we'll represent it with x. And we know statements like every, for statements like every or everyone, or statements like all, we're going to have a universal quantifier. Therefore, we'll represent it with a single statement, which is going to be this, which means, so we're going to replace it with a single statement, which is Jonathan takes every subject. For all x, Jonathan takes x, which means Jonathan takes every subject. Now, if you had to represent something like everyone takes every subject, how would you represent this? We know that for a statement like Jonathan takes every subject, we represent it with something like this. Then in our class, we have people like Jonathan, Mark, Carla, uh, John, and all such people. And for everyone, we'll represent it like this. For example, for all X, Jonathan takes every subject. Then we have again and for all X, Marla takes every subject, and for all X, Mark takes every subject, and this goes on and on and on. So the thing that we saw remains constant is like this. For all X, Jonathan takes. So here we see for all X takes, and this remains constant. This over here remains constant. This over here remains constant. So the only thing that we saw varying is this, which is the person who is taking these subjects. Therefore, we'll represent it with a variable called y. And the statement could be represented like this, which is for all x takes y comma x, and everyone takes every subject. So this is how we represent this. For all y and for all x, y takes x. It is a representation of this thing, which is everyone takes every subject. Okay. Now with this knowledge, let's try to represent these sentences, which is someone takes some subject. So we should start with the basic. Let's consider this thing. John takes. How can we represent John takes some subjects? It's going to be an existential quantifier, and then John takes x, which means x is a variable, and here this existential quantifier means that he's taking some subject. But here someone takes some subject, which means that there is at least one person who takes some subject. So outside this also we will have an existential quantifier. So this will become takes. We'll represent this with y and x. So this will become like this. So this gets changed to this because we here the person is also now represented with a variable y. So this means, so the thing which is inside this bracket means y takes some subjects, and this existential quantifier in addition to this means that someone takes some subject. Now let's try to understand this problem. Someone takes every subject. How would you represent the basic thing, which is John takes every subject. John takes every subject. Let's try to represent that. It will be represented like this. John takes every subject. So we're going to have an existential quantifier here. But we're not talking about John. We're talking that it could be John or more people, which is some. There is at least one. So this gets converted into y. Now this will be also a variable. And outside this, we're going to have an, sorry, existential quantifier. Because we're talking about some. Now let's try to solve this problem. Everyone takes some subject. So again, we'll take the basic one, which is, for example, John takes some subjects. Some subjects. But here we're talking about everyone. Therefore, outside this, we're going to have a universal quantifier. And this will also be represented with variable because we are talking about many people, which means everyone. So this gets changed into y, and x takes, so y takes x subject, and this means y takes some subject. But here we are not talking about single entity, we're talking about many. Therefore, it gets changed into, for all y takes some subjects. That's how this gets changed. So the basic approach is, if you are getting a bit confused, you can just solve it in a single statement. But if you are getting confused, take a basic uh, statement where to take an example of a person taking some subjects, or a person taking every subject. Then you can build it further. So let's try to solve this problem, which is every subject is taken by someone. So it's different than what we discussed previously. Um, so let me write it down for a basic case, which means every subject is taken by someone. Let's write here, networking is taken by someone. Taken by someone. So in the previous examples, we were talking about a person. For example, Jonathan takes networking, but here we are talking about networking, which is taken by someone. So this is how we will represent this. But here we're not talking about uh, a single subject networking. We are talking about every subject, so we could represent it like this. So in this case, this networking will also become a variable. So this will remain as it is. This remains as it is. This becomes a variable y. And outside this, we will have a universal quantifier, which is for all y, which means every subject is taken by some one. Okay, so this represents every subject. So this represents every subject, and this represents someone. Okay, now let's talk about some subject is taken by everyone. So it's quite easy now. If we have to represent uh, a a subject is taken by everyone, how would we represent that? It's by this. Let's talk about the base case, which is networking is taken by everyone, is taken by everyone. It's going to be a universal quantifier because we are talking about everyone. Now, to represent some subject is taken by everyone, this also just becomes a variable that we represent y. So the upper statement gets changed into separated by comma y, and it gets changed here like this. It remains as it is, and it becomes an existential quantifier. This means some subject, and this means everyone. So some subject is taken by everyone will be represented with this kind of representations. Now we are left with this, which nobody takes every subject. It's a bit tricky. Now let's take an example where John takes every subject. John takes every subject. We'll represent it with this, where we have universal quantifier. So this means John takes every subject. Okay. Now here the statement goes like nobody takes every subject. So nobody means that everyone is involved, and John is also a person among them. So when everybody is not taking every subject, so John is not also going to take every subject. So we will have a negation outside this. Okay. So we're talking about everyone. Now John over here will get replaced by a variable y. So this gets modified to this. So since everyone is involved in this, it gets modified to y. So this means that nobody takes every subject. This means John doesn't take every subject. Since everyone is involved, we represent it with a variable y, and it means that everyone is not taking every subject. So that was all. Thanks for watching.